In fact, let me go ahead and set that up as a separate thing. So our very interesting things we are going to do today. First off, let's go ahead and get, well, I'm not going to bother pulling up the slides. I'll just simply show you, right? So the last thing I wanted to there's a couple things so we've gone over quick select, right? Does everybody understand kind of how that works? Right, the reason it's more effective than we can do that a bit quicker than quicksort because of the ability to, because where quicksort we have to go down both branches of the partitioning. In quick select we only have to go down one branch. And again, O of n squared worst case scenario, but that's very rare. So on average we're looking at O of n. Okay? Similarly, so matrix multiplication, first off, right, we've got the product of, you've got n squared items, each of which take O of n time to compute. Okay? Just, so our upper is O of n cubed, right? Our upper bound is O of n cubed. In 1969, it points out, Volker-Strassen found a more efficient algorithm where the idea here is that if you split it into 4 blocks, so just like how we split with our division algorithm, okay? So this is all I'm going to say on the subject. Just like the division algorithm where we split it up into half bits, right? And then we ended up with, we went from 2 multiplications to 4 multiplications, and then we did some clever math to, instead of doing 4 multiplications, we go to 3. Here, you split it up into 4 blocks, just, of each of n over 2 by n over 2, so each getting a quarter of the grid, right? You multiply those together, and it turns out you can multiply those blocks together just like you could single elements. Okay, just like, so you could split up into the problem up into 8 quarters, just like you could split up a single item into 3 halves. And then so that gives us, with 8 matrix multiplications here, that's 8 subproblems, each of half the size, t squared, which works out to O of n cubed. But the magic happened here with this runtime, which is that somebody figured, which Strassen figured out that you could do some clever math. So so here, right, we have our A, B, C, D, E, F, G, H. So he now has 7, so he figured out 7 multiplications. 7 matrix multiplications. Okay. And then said, oh, if you do these 7 multiplications in these orders, you get the answer, which brings it down to 7 problems of half the size, which improves the runtime to n to the log base 2 of 7, which gives us 2 to the 0.8. In fact, it's kind of been a race to the bottom to see how well we can go. So I guess I will pull up the slides very briefly on this. On fast multiplication. Divide and conquer. Long story short, divide and conquer is a very powerful technique. And sometimes you just need to, sometimes what it takes is that we need to formulate a good way of doing the multiplication. You're right. First step of divide and conquer is formulate a way to do it as a divide and conquer algorithm. If that ends up giving you the same runtime, somebody else might come along and figure out, oh, but I can reduce the number of subproblems. And then suddenly it becomes a lot more efficient. So as time went on, we've been able to drag this down. And again, I don't think you'd be able to get to n. I don't think it's possible to get to n squared, but there are here the number of floating point operations to multiply those. And it's so, which as again, we're not dealing with n-bit operations. These are floating point operations. All right. So we're going to talk about graphs. now. I think now is a good time to jump ship and talk about graphs. And I also decided maybe we'll pivot a bit because you've learned graphs, right? You've learned them to death. Okay, so how much have you learned Python? How much do you know about Python? You're great with Python?
I'm okay with it.
Okay.
I'm okay with it.
Okay, so let's do a crash course into Python. To get Python, if you installed on your computer, you just simply go to python.org. If you're on Windows, download the latest version of Python, and when it asks you to, and after you download it, you run it. On a Mac, it should come pre-installed. Customize installation. Just be sure to check these optional features, specifically the pip, and also putting it in path. Which is really important to put it in the path, to enable it to be in path. Now, why do you care about this path that I'm talking about? Path, if it doesn't work, by the way, if this next part doesn't work, just reinstall it and just look for the appropriate option to check. It's very easy. So for path is what enables you to do something like this, which is either you type Python from the command line and access it, or to type what we're going to need, which is pip, P-I-P. Okay. By default, Python comes bundled with idle, which is not bad. It's certainly a nice and brighter way to interact with it rather than just the command shell. And you can get a lot done just by interacting with the Python in this nature. I tend to use VS Code for stuff. So Python files are .py. Python files are .py, and the biggest thing, Control save as. Save as .py. The main thing to understand about Python is that it's a lot looser of a language than Java is. And the reason I'm introducing Python is because I want to show you NetworkX, because I figure maybe then I can give you some more interesting programming problems rather than giving you rather than giving you more of the classical math homework. You might appreciate that. Okay? Because I do know a bunch of Project Euler problems that deal with graphs and stuff like that. But anyway, so first off with Python, basically it's like a script. It doesn't start at any specific point unless you have this specific line in this. If name equals main, then what's inside the if statement will get treated as like the main class, and it will only activate if you're running this file. Okay, it will only activate if you're running this file. If you're importing this file, then this won't get called at all. Okay, next big thing about Python. So going from again. Basic kinds of variables. Python doesn't really care how big your integers get, right? We know that. It doesn't have longs or anything like that. It's just numbers, right? And again, I'm going through this quickly because you all know, because you've all had some exposure to Python, right? Okay. Next we have doubles, right? Which work exactly like doubles in every other programming language, which means that they use the IEEE double precision floating point, which basically means that this is in a really interesting scientific notation. That does lead to some quirks, right? Have you all seen what happens if you do this, right? 0 plus 1, right? Print, right? It does lead to some interesting quirks, but that's not unique to Python. 0.3, and it just has to deal with the inaccuracy of trying to encode numbers in this scientific notation, numbers that aren't cleanly, and we're going from base 10 to base 2 to base 10 again. So it's It's the same kind of issue you'll run into if you're trying to represent 2/3. This is essentially just machine error. So it happens rarely, but you'll need to be aware of it. Again, I'm going quickly. Character, right? Strings. There are no characters, there's just strings. Strings are iterable, meaning you can iterate over them. Right? We can do A, B, C, D, E, F, G, H, I, J, J, right? We can iterate over each of them and we can index them. Print S, the third character in it, so this will print C, and Python supports negative indexing, which means I can do this and get the last character. C and J. Make sense so far? Okay. Probably also very useful is the slice notation. Yes, no? Slice notation? Slice notation.
Yeah,
Slice notation of Python is pretty awesome. Basically, it's like substring. So from the beginning up, so this says from character 2 up to but not including character 5, or character 7, every other character. C, start at index 2, every other character. E, G, up to but not including character 7. So you can leave any of these blank to go by their default variable. So if you leave out the third argument, it just goes up by 1. If you leave out this, it goes to the end. From beginning to the end. And of course, my personal favorite is being able to do stuff like that. Negative from 3 from the end to the beginning. So being able to get the last 3 characters of this is actually of something is fairly trivial in Python. It's pretty cool. By the way, everything I just showed you that works on a string works on a list. Lists are array lists, right? So they're just array lists, but they can be treated, but they use indexing notation. If you need to add something, if you need to expand your list, there's a couple ways to do that. One way is to just simply add another list to it, and it will concatenate those lists. Also, Python supports multiplication of this, which is also concatenation. So if I need an empty array of zeros, if I need an empty array of 100 zeros, I can get that very quickly. Otherwise, if you want to add an item to an array, it's fairly straightforward. You just use append to add to the end, and that expands the capacity of the array. Make sense? Well, it adds it expands the size of the array list. It does not change the capacity unless it needs to. Okay. So, all right. The only other thing I should mention is that, the only big thing worth mentioning is that Python instead of hash maps, it has dictionaries, which is the same thing. They just call them different. Okay, so if you remember hash maps, the big thing is that with Python, guess what? You can just use key value. You can just use whatever you want. Sorry, you can use whatever you want as it's basically it uses index notation is what I'm trying to say, and spent like 30 seconds trying to say. You use the same kind of notation you would use for this. For a list, which keeps it nice and consistent. Right? Key value. And you can add as many arbitrary key value pairs as you want. The final operation is, the final thing that's worth mentioning is this. Just being able to create a set. A set will be extremely useful as we're going through graphs and trying to do graph algorithms because because typically what we use this for is visited, and then asking if X is in visited, which works like the mathematical in. Is it a member of this set? Make sense? So anyway, that's probably all stuff you knew, right? Use def to define a function. You all know that stuff. Okay. Great. So so basically with NetworkX, what you need to do to install it is you do pip install NetworkX, and that will go and gather what it needs from the internet to grab at NetworkX. Also worth installing at the same time, since you're already here, is pip install matplotlib, which is the math plotting library. It's very, very powerful for generating stuff, and it's going to enable us to install a bunch of other things. By the way, it's going to enable us to do graphics with our graphs. By the way, installing this will also automatically install NumPy for you, or NumPy, which is basically you use R or NumPy for doing statistical work. It's one of the two these days, from what I understand. Or maybe something else. I don't do those kind of works, but from what I understand, those two compete with each other. Now, NetworkX allows us to do a lot of funky things. So first off, let's take a look at our imports. So this is one program I just simply cobbled together last night. Okay, so this is a complete graph of size 10. I'm going to go ahead and generate one of size 5. It's easier to see what's going on with a complete graph of size 5. Okay. So NetworkX is as next. So basically when you import a library, to use something in it, you have to do library name dot something. The as allows us to give it a nickname. So when I want to generate a graph, I can just simply do nx dot and then generate a graph. Here I asked it to generate what's called a complete graph, shown here. So looking at this image, what do you think a complete graph means, right? Yep, all the nodes have connections with all the other nodes. If we're looking at something, so this is a concept in graph algorithms called a clique, or it refers to a, and I'm just double checking to make sure that I'm not going to, a clique is essentially a subset of that. So yeah, is a subset, A clique of a graph is an induced subgraph that is complete. Basically, this is a clique, is what we're saying. So let me go ahead and try adding something on my own. Let's see, can I add to this? G.add, let's see, let me stop this code. G.add underscore edge 0 to 1. Will that work? I hope so. Let's see. Okay. Oh no, it's already got a 0 in there. So I'm going to have to generate a 5 to 1. Okay. So I've modified this complete graph fairly easily. Okay. So we look at this, and this part of the graph, what we call 0, 1, 2, what's connecting nodes 0, 1, 2, 3, and 4 together is called a clique, where every node in that component is connected to every other node in that component, in that subsection of the graph. That's a clique. Essentially, in other words, it's a subsection of the graph, which is a complete graph if we were just looking at it. There's a bunch of different kind of special graphs, complete graphs, bipartite graphs. planar graphs. There's different classifications of graphs and the like. Okay, but for this for graphs, it's fairly straightforward. With Network X, we can basically say, hey, I want to generate a graph. And there's a bunch of different subgraphs that we can generate with that are built in. You can either create one from scratch, and then you can say, hey, I want to add edges and vertices to it, right, like this. So for I in range 0 to 5, or rather in range, let's go ahead and say, bringing for I. Sorry, I'm just thinking of a clean way to do this. Oh no, there's no need for a clean way to do this. For letter in A, B, C, D, E, G dot add, and here it calls them node, so I can just simply say, hey, add this letter to the graph, and then I can draw it, and it will be happy to basically create a bunch of nodes, which are all disparate from each other, right? We can see that they're labeled A, B. It's a bit hard to see, I'm sure, from there, but A, B, C, D, E, it gives them a label. And then if we wanted to connect them, we could do G.add edges, add edge, and then we'd say, from which two edges do you want to add? A to B. If the nodes you want to add doesn't exist, then it will create that already. And here we go. A and B are already connected. What? Delay the page? Delete the edge? Yeah. Probably. G dot remove edge. Yeah, you can remove an edge. I mean, it would be very odd if you couldn't, because this is a very robust library. Besides creating this, which is useful for dealing with our own problems, right? Network X also has a bunch of problems has a bunch of things that are extremely useful. I haven't figured out how yet I want to use this library, incorporate our what homework assignments to really use yet, but it is extremely, again, robust, right? Here it says, hey, you can make, in this tutorial, you can read this tutorial. It has a lot of graph generator functions, it says. So Graph Atlas, which has a bunch of graphs, apparently, pre-generated graphs from something called an atlas of graphs. So we can actually try that. So n dot graph atlas, and let's try number 5. Okay, and that's apparently graph number 5 in the graph atlas. Let's go with 99 and see if it gets any more exciting. Oh, slightly more exciting. So in other words, there's already a bunch of pre-made graphs if you need a graph to test a random algorithm. Okay. Let's see, circular, balanced tree, barbell graph, binomial tree. Doesn't have any bipartite automatically that I can see here. Lattice graphs, which are pretty cool. Let's take a look so lattice graphs are actually pretty interesting, which they look like grids. Probably one of the most famous papers about lattice graphs was this, routing in a small world. It's one of those papers which is interesting because it was only 1 page long. Here it is. This is the, oh, come on. Really? There it is. Navigate, this is the entirety of the paper. And this is what we call a lattice graph where in a given node U, it has connections with A, B, C, and D. And this was basically looking at what happens to the routing time, to the runtime that you need to route from A to B. If every node had a single random long distance hop, long distance connection, and based on the clustering exponent, it's actually very interesting. He shows that it's log n squared. But regardless, so lattice graphs are actually very interesting kind of designs for this. Now, I like graphs because, first off, in terms of problems, if they're using my homework, by the way, for big O notation, they may have this. You may have seen this. I don't know. Mazes. They are graph problems. This is asking you to find something called a Hamiltonian path, or also known as a Rudrada path. Basically looking for this puzzle, if you read the rules at the bottom, tells you want to look at each node, you need to visit each node once, and you need to visit each of these nodes once, and you can't visit any single edge more than twice. A lot of these puzzles, maps and mazes, basically reduce to graph problems, which is pretty interesting. Especially, or not all of them, but like, let's see, this one, which is all about an economy based off of trading geese. So basically, and the flags denote down here how many geese you can purchase, how many geese you're taxed on, and so forth, and you want to try to get to the castle. So what is the appropriate... You can see this is a graph problem, where basically the weights have... But here with the paths, the weights have kind of been shunted onto the... Sorry, the cost of traveling through stuff has been shunted from the edges to the nodes, right? Which is kind of interesting. Or the way you would model... How would you model that? Directed graphs with edges, with edges and weights. Again, graph problems go over a lot of things, and your slides actually our slides talk about that. It also wanted to talk about universal hashing. I don't know why it wanted to bring up universal hashing here. We'll bring that up some other time if we need to. But we can talk, but there's a lot of interesting problems you wouldn't think about with that turn into graphing. For instance, graph coloring. The idea here is that in a world map, every country needs to be colored differently in order to distinguish it from its neighbors, right? So, given a map, what is the minimum number of colors we can use to color this graph so that no two countries share the same? Sorry, how many colors do we need to make sure that no country shares a color with its neighbor? It's a very interesting problem. It's a graph. That's called a graph coloring problem. We've seen maps like this with COVID-19. That's also graphs. But generally, kind of graphs like this that deal with these kind of things are undirected graphs. And what, again, it says is captures pairwise relationships between objects. And that term, relationship, is probably the most abstract thing we can have, because everything's a relationship. Everything. From it can go from, because one of the things we can look at graphs is that, yeah, you can look at it as a relationship as how you get from one point to another. That's the standard kind of way we look at things. But it's also, friendship online, whether or not you're friends with somebody. We can, it's the cost, the amount of profit, the amount of money the conversion rate from one currency to another. A lot of these things are useful. And then we can, here is, the Enron, 1 week of Enron emails. If you aren't familiar, Enron was a huge kind of business scandal back in the day. But there was a lot of email evidence connecting and so basically the email and from the litigation is very popular for doing analysis in a lot of different fields. Biological networks. The internet map, one of my personal favorite. This is what's called as, this is often referred to as what's known as a, do you know what it's called? It is called a scale-free network, I believe. Scale-free network. I mean, I used to study this stuff through my PhD, but I've forgotten half of it. Yeah, there we go. It's where, so scale-free network is a network whose degree distribution follows a power law. Part of network science. In other words, things like the internet. Scale-free networks are things where where nodes have a high degree. Do you know what degree is? Yes, no? Easy to define, no problem. So see this gray node over here that I'm circling?
The number of edges?
Yep, it's the number of edges that are here. 1, 2, 3, 4, 5, 6. Another way is saying how many nodes it's connected to. It's connected to. So notice that there's a number of. In scale-free networks, essentially you get hubs, nodes that have unusually high number of connections. You can see why that's important for the internet because, you have giant services that connect to everything. Not pictured is Amazon. Why is Amazon not pictured in here? Oh my God. There's an issue when AWS goes down for a reason, Amazon Web Services, because it's connected to basically everything. Social networks, who's connected to who. Right, there's tons of things here. Games, forward position, going from one legal move to another. That's kind of what we look at with Rubik's Cubes, with basically going from one position on your board, one position of a Rubik's Cube, rotating it to get to another position. There's tons of graph applications, basically almost in a lot of ways that a lot of problems can be trivially solved with application of hash tables. A lot of problems can be trivially represented as graph problems, which is useful because then once you transform it into a graph problem, you have a whole lot of tools to do stuff with it. So did you go over the graph representations? The two ways that graphs are stored in memory? Yes or no? Adjacency list versus adjacency matrix? Excellent. Okay, adjacency, so it goes over adjacency matrix first. First off, basically you need to have some way to represent a graph as like a data structure, right? So there's two different ways, just like array, and they both have their benefits, just like array lists and linked lists have different benefits for different use cases. So in this case, a graph, this graph over here, is represented by a 2x2 matrix, and this is an undirected, unweighted graph, so we use a 0 in this case to dictate the absence of an edge, and 1 to dictate the presence of an edge. So we're asking, hey, from 1 to 2, is there an edge? Is there an edge going from 1 to 2? So notice there is one from 1 to 2. And then, yep. So, and over here, you've noticed that. Now, one thing that you may not find in these, but is actually common, is that you do get, especially in if you're talking about discrete finite automata, is this, which is that you do have nodes that have self-referential edges. That's common in discrete finite automata, which are essentially regular expressions. Okay, and then you learn the other way, which is that you have adjacency lists. For each node, you have a linked list, right, with containing all the edges. So this one obviously takes, if you have this number of nodes, then it takes this much space, right? So checking to see if there's an edge from U to V, from any node U to V, that's a constant time operation because that's just a lookup in a matrix, right? And looking up something in a matrix is constant time. Okay, checking all the edges, well, you have to iterate through the entire n by n matrix to identify all of them, so that takes n squared time to read out all those. Okay, an adjacency list, space required is you have a linked list for all n. Let me rephrase this in terms, right? We have V linked lists, right? And then, so that's at least one. And then we have, then plus E for the number of edges, because each edge takes an entry in a linked list. Okay. Iterating through this takes m plus n time, and then checking UV, it takes long, but it can take longer, especially if you're working in a scale-free network, but you might not be. Now, the question you may not have covered is, when do you use one versus the other? Any remembrance of that? Ring any bells or no? When do you use one versus the other? Adjacency list versus adjacency matrix. When you should use the adjacency list and when should you use the adjacency matrix?
And then list used when there's some data
It doesn't have to do with that. Yeah, either one works. Either one works. It just simply,
it's about space computing?
it has to do with space and efficient use of space. So you use this one for dense graphs. And you use this one for sparse graphs. And the idea here is that basically is that you use this when, so you use this when the number of edges is proportional to the number of vertices squared. In other words, if this matrix is pretty filled up. Make sense?
Oh, yeah.
Okay, if you're using the, and on the other hand, if you've got a linear relationship between the number of vertices and the number of edges. Okay. So, if it's more linear, why do I keep drawing an O? I don't need an O, I just need E. Right? If it's more of a linear relationship, then all we do is then we use a sparse, this, and it's sparse. The tipping point, according to our previous textbook, which from Kaufman and Wolfgang, because I don't think your textbook necessarily goes into it, is 25% usage of the main. Once 25% of all possible edges exist, right? So all possible edges. In other words, this dictates all possible edges. Once this is 25% of the way filled, if this would be 25% of the way or more filled up, it's a dense graph, so use the adjacency matrix. Or you want to use, 25% of v squared. That is the heuristic I have from our previous textbook of Kaufman and Wolfgang.
So how do we apply these in real life? Do we check the least squared every time?
You could. In some graphing algorithm, so let's see. Let's go ahead and see. Network X dense graph. So the idea here is that basically so it returns the density of the graph. So when it generates a graph, collection of nodes, let's see, is hashable, okay. I'm trying to figure out what it does. I read that, I thought this was a sparse graph, but I'm not sure. Generally, though, if you're using Network X, I would let Network X handle it. Adjacency. So it's got an adjacency dictionary, it says in it, which makes sense. That's because. So I'm pretty sure it uses its own thing because, The graph class uses a dictionary of dictionaries of dictionary data structures. The outer dictionary holds an adjacency information keyed by node. The next dictionary, adjacency list dictionary, holds a adjacency information and holds the edge data keyed by neighbor. In other words, it doesn't really. In other words, it's telling you it's figured it out. Don't worry about it. So in practice, let this handle it out. Yeah, I mean, and you're also using Python, so optimization was kind of out the window to begin with. Now, if you were doing this in Java, Jung, that has a way of dictating whether or not you're going to be using a sparse graph. You can dictate whether it's a sparse graph or not. You know, I'm sure I'm not an expert on Network X, but I'm sure that it's got that I'm sure that basically they've thought of everything here. Okay, this is again the very robust data structure. They are more concerned about, okay, which should you use? Directed graphs versus undirected, and multi-graph versus multi. Multi-graphs are graphs where they are not going to really be covered, but they're graphs with multiple edges. For instance, there's multiple ways to get from here to New York City, each having their own particular attributes and different ways of going. Okay. So a couple of terminology. A path is basically, it's a sequence of nodes such that every pair is connected, right? The sequence of nodes where everything is connected. Okay, every single consecutive pair, rather, is connected. It can repeat. A path can have, like, I could go from, for instance, a path could go like from here to here to here to here to here to here to here, right? Or even better, or if all nodes are distinct, I could go from, if I don't want to repeat an edge, which I probably shouldn't, for just to not overcomplicate things. This is a path, right? Notice that I visited 2 twice, right? That is, a simple path is one where basically I don't visit where every node is distinct, okay? Undirected graph is connected if you can get from every point to any other point, and then if you can't, well, a graph can be separated into connected components. Right? If I wanted to turn this into a connected graph, it's just as easy as drawing drawing in these edges. And now it's a connected graph. Cycles.
Professor,
Yes.
can we have a break?
Sure.
Okay, great. I'm sorry, I'm like falling asleep like halfway through the lecture.
I'm sorry. Is it me or
Oh,
just...
I don't know. Something about this room.
It's nice and cozy, right?